All right, here we go. Okay, so 1.3, properties of limits. What we're going to talk about here with properties of limits is, remember in the past we said there were different ways to show, like to find a limit, numerically with your table, graphically with the graph, and then the third way is algebraically. So today we're going to talk about the algebraic way. In a lot of cases, it's the fastest, easiest way to do it, especially for certain types of equations, okay? So you're going to definitely like these first ones because they're pretty easy. So let's get started. You have learned that the limit of f of x as x approaches c does not depend on the value of f at x of c, right? We've talked about this. It could be that the value doesn't exist, there's a hole there, but the limit still exists, right? But it also could be when it's like a straight line, or that it's a quadratic or something, and that the limit is precisely equal to the value of your function there, right? In such cases, the limit can be evaluated by direct substitution. So basically, in these types of graphs, the limit as x approaches c of f of x is just equal to the value of the function right there. So you can just literally substitute it in. You just take it, plug it in. This is what we were doing on those tangent equations yesterday, right? Such well-behaved functions, and that's what we're going to call these because they're nice and well-behaved, have to be continuous at c. We're going to talk about the definition of continuous, but it really is just what you would think. It means that it continues right through that point. There's no holes, there's no asymptotes, there's no crazy weird jumps or skips or anything like that. Okay? So basically, let's go through some basic limits. Theorem 1.1 says that let b and c be real numbers, let n be a positive integer. If I have the graph, the limit of x, as x approaches c of just b, what kind of graph does that look like? Straight line, don't say straight. Horizontal line, right? Yes, all lines are straight. Horizontal line at b, right? So every value is just equal to b. So the limit at any point is going to be equal to that b. Okay, so that's all that this first one is. What does the line x look like? Diagonal line, yeah, that way, right? Okay, so we've got our line, right, our straight with a slope of 1. So the value there is just going to equal c, right? At 2, it's equal to 2. At 5, it's equal to 5. At 7, it's equal to 7, right? So you're just going to get the value of your c. And then for any sort of x to the first, x to the second, x to the third, these are basic polynomials here, power functions. You can just plug it in, and it'll be the value of that function as well. Okay? So these are basic ones where we can just do direct substitution. So number 1, what would be the limit as x approaches 2 of 3? 3. It's always 3, right? If I think about this graph, it's at 1, 2, 3. This is the graph of that function. So as x is approaching 2 from both directions, well, it's going to be 3. Okay? Nice and easy. How about this guy? As x is approaching 4. Very good. This is my graph. So as I'm approaching 4 here, I'm going to be approaching 4 there. So the limit, again, these are just these ones functions where it's equal to the value of the function. How about for x squared? Naomi, go ahead.
Number 2, it's approaching negative.
Oh, thank you. I didn't even see that. So then the answer would be? Negative 4. If I had lollipops, I'd give you one. What do I have? I think I have some candy for you, Naomi. Stop by after class. I'll get you something. So it should be over here at negative 4. Thank you. As x is approaching 2 for this one, right? X squared. So what's the value of my function? 4. So I'm just literally direct substitution, right? I'm plugging it in. 2 squared gives me 4. Okay? These are nice, well-behaved, simple, continuous functions. All right, properties of limits basically say, and you can read this whole chart down here, let b and c be real numbers, and let n be a positive integer, and let f and g be functions with the following limits. So it's basically saying the limit for f is L, and the limit for g is k. Okay? What it's talking about here is that basically scalar multiplying by just a number, adding the 2 together, multiplying the 2 together, dividing the 2, raising 1 to a power, you are going to be able to do all of these functions across the limit as well, right? So since these are nice functions, I can multiply by b, then I just have to multiply the limit by b, and it's just b times the limit. It'll be the same thing, right? What does that mean? So like if I had the function x squared, and the value was 4, like in that last example, right? That was my limit, was 4. And then I wanted to do 5x squared. We'll just take 4 and multiply by 5. And your answer is 20, okay? So scalar multiplication works across limits. Multiplying or adding 2 of them together. So if I add the 2 functions, x plus x squared, then I can just add their 2 limits and get that answer, okay? Multiplying them, I can multiply them and get it. Division, as long as your denominator doesn't equal 0, you can divide them, okay? Raise 1 to a power, it's the same thing as raising the power. Okay, so that's all that table says. So let's look at the next page to do some examples of those, using properties of limits to rewrite each limit expression. So basically what you want to do is you kind of want to, and again, as you get better at this, you're not going to have to go through all these steps. Later, you're just going to be able to directly substitute these in. But for now, we want to see how it does break down. Technically, this would break into the limit as x approaches 3 of 5 times the limit as x approaches 3 of x squared. All right? I'm basically splitting that up into a multiplication problem, right? It's a product. So I'm splitting up the 2 limits then. So what is the limit as x approaches 3 of 5? It's just 5. And what is the limit as x approaches 3 of x squared? We'll plug in 3. 3 squared is 9. And my answer is 45. A lot faster. Just take this 3, plug it in here. You're going to get the exact same answer. Okay? So as you are doing these on your homework and as you're going through and practicing them, you're just going to directly substitute them in here. Okay? But what I'm showing you is that where does this come from? It comes from the fact that product does carry over to limits. Same idea here. You can split this up into the limit as x approaches -2 of 6 plus the limit as x approaches -2 of x plus the limit as x approaches -2 of -x squared. All right? And then you can just plug those all in. So the limit here, the first one is 6. When I plug in -2, it's -2. -2 squared is 4, so -4. And again, it's literally the same thing as directly substituting in for all of these. Okay, so you'll get 0. All right, for the limit of that whole thing. Okay, you kind of see where this is coming from. So again, as you go through and do these, you aren't going to have to do this every time. But for now, I do want you to just see where the properties of limits come from. Okay, so this would just break up into x times the limit as x approaches 1 of 3 times the limit as x approaches 1, bless you, of x to the 4th. What this should remind you of kind of is log properties. And when we would split up and condense and expand all those log properties, it's kind of the same idea here. So then that first one is just 1. The next one is just 3. And then just 1 again. So 1 times 3 times 1. And I just get 3. For this one, notice that whenever it's a quotient, you want to double check that denominator. So if I have a 5 and I plugged it in, it would not make my denominator equal to 0, so I'm okay. All right, so then this one would split up into the limit as x approaches 5 of my numerator divided by the limit as x approaches 5 of that denominator. Right, just a division problem. So for this first one, I can split that up again into addition, right? And I could split this one up again into subtraction and go from there. In the interest of time, we're just going to plug in. And what will I get? I'll get 5 plus 3 divided by 5 minus 2. And I'll get 8/3. So again, splitting this guy up, I'd have the limit as x approaches -4 of x minus 5, and then take that whole limit and square it. And again, then you could split this up again. You could split it up one more into subtraction, okay? But again, saving some time, let's just plug in. So I'll have -4 minus 5, that whole thing squared. And my limit is 81. Okay, so hold on, we're pausing for a second.